Hello everyone. In this video we're going to talk about complete binary trees. Here you see four examples, T1, T2, T3, and T4, four complete binary trees. The T1 tree has the height of 1 with only one node. T2 has 3 nodes, and so on. So let's go to the definition of the complete binary tree. A complete binary tree, first of all, is a binary tree. It means that each node has at most 2 children, the left child and the right child. And in a complete binary tree, each node except the leaves has exactly 2 children. So in the tree T1, as you see, the root node is the only one that we have, and also at the same time it is a leaf, so it is a complete binary tree. T2 and T3 and T4 also are complete because each node except the leaves, as you see, have exactly 2 children. So we're going to see some exciting features about the complete binary trees, such as the number of nodes or the height of the trees in a complete binary tree. So here, as you see, T1 has a height of 1, T2 has a height of 2, and so on. So we're going to find out a pattern to find out what's the number of nodes in the complete binary tree. So I'm going to start with the T1. So let's see if we can find the pattern. So in T1, the height of the tree is 1. And the number of nodes, which I'm going to use n for indicating that, is equal to 1. In the T2 tree, we have the height of tree is equal to 2. As you see, these are the tree. So height is 2, and n is equal to 3. So t is equal to for T3, the height is equal to 3, and the number of nodes is 7. And T4, the height is equal to 4, and the number of nodes is equal to 15. So sometimes when dealing with some patterns like this, we might able to easily guess what's going to be the result. Sometimes it might be hard. Might be hard. In this case, the pattern is n. So I'm going to just erase this one here. N is equal to 2 to the power h minus 1. So that's the number of nodes in a complete binary tree with a height of h. So h again is the height of the tree, or again height of the tree is the number of nodes from the root up to or down to the depth of or the deepest like the node in the tree. So and this is complete means that the distance from the like the root to every leaf is exactly same. So as you see in the T2, the distance between the left child from the root to left child and right child is exactly same. Same for T3 and T4. So that's another feature of like the complete binary trees, that the distance from the root to any leaf is exactly the same, and it is the height of the tree. So we just guessed that the number of nodes in the complete binary tree is equal to 2 to the power h minus 1. Again, h is the height of the tree. But let's see that how we can actually prove these guess. It's just part of like the things that we did. We need to actually to prove that. So what I'm gonna do, I'm gonna start with just writing down what we have here. So when h was equal to 1, when the height of the tree is equal to 1, we have a complete tree of height 1. So we had only one node at the root. One node at the root. When h was equal to 2, we had one node at the root plus the 2 children for the root that we had. So if you go back to the T2 here, you see that the root node has exactly 2 children, so the number of nodes becomes 1 plus 2 is equal to 3 children. In the in the T3, which is a complete binary tree of height 3, as we see that, so we had one node at the root plus 2 children of the root and each child of the like the root, as you see, like this one and this one, both of them also have 2 children, so it's going to be plus 2 times the number of children that we had here, so 2 times 2, so it's going to be 1 plus 2 plus 4, which is equal to 7. So if we continue that for h equal to 4, we're going to see the number of nodes going to be 1 plus 2 plus 4 plus is number 4 plus 7, which is equal to plus 8, excuse me, plus 8, which is equal to 15. So we can conclude that the number of nodes for the complete binary tree follows a pattern, so which is 1 plus 2 plus 4 plus 8, and as we see here, this number 8, or let's just write it another way, so it is equal to 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3. For the height equal to 3, it was 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2. For height of 2, it was equal to 2 to the power 0 plus 2 to the power 1, and for one node, it was 2 to the power 0. So let's look at the highest power, or the degree of these expressions that we are writing here, and compare it with the value of h. So as we see here, the highest degree is 3, which is exactly 4 minus 1. With the height is equal to 3, the highest degree is 2, or the degree of the expression is 2, and it's exactly a height of the 3 minus 1. So that's a pattern that repeats. So we can conclude that in a complete binary tree of with the height of h, so for h in complete binary tree, the number of nodes is equal to 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power h minus 1. Now what we need to do, so we found that this is the formula for the number of nodes in a complete binary tree, and now we're going to see that how we can actually prove that it is equal to the power h minus 1. So what I'm going to do, we are going to just say it is equal to 2 to the power h minus 1. However, we need to prove these theorem. So we're going to use proof by induction technique in order to prove that this 2 to the power 0 plus 2 to the power 1 up to 2 to the power h minus 1 is equal to 2 to the power h minus 1. So I'm going to just simplify the way that we are writing this x1. So I'm going to use the sigma notation. So let's use the I as an index. So from I equal to 0 up to h minus 1 of 2 to the power I, we should say that it is equal to 2 to the power h minus 1. So let's prove this together using the proof by induction. So as we know, the proof by induction has 3 steps. The first step is the induction base. The second one is like the induction hypothesis, and the third one is just to prove the the formula based on the induction base and induction hypothesis. So for the base case, I'm gonna use h equal to 1, as we know. So when h is equal to 1, we know that n is equal to 1. So going back to the T1, as we know that there's a number of nodes is 1 and the height is equal to 1. And look at the formula, we see that, so sigma of I equal to 0 up to 1 minus 1 of to the power I. It is equal to only to the power 0, which is equal to 1. So for the base case, it is true. So the first step we're done. We showed the induction base, and now let's go to the induction hypothesis. We're assuming that for a complete binary tree with h is equal to some numbers such as k. So we're choosing k as a random integer number, random positive integer number, and we're assuming that for h is equal to k, n is equal to the power h to the power k minus 1. Or in other words, we're going to show that the number of nodes is equal to this theorem that we had here. So based on the hypothesis, we're going to say that from I equal to 0 up to k minus 1 of to the power I, it is going to be equal to the power k minus 1. Now, if we can prove that for some numbers k plus 1 it is true, then we can conclude that these two sides of equality are equal to each other. So here we're going to use induction hypothesis and also induction base to show that. So let's see what's going to be the number of nodes in a complete binary tree of k plus 1. We learned that when we are doubling or we're adding another like level to the tree, complete binary tree, the number of nodes that we have will be will be added by the double of the number of nodes that we have in the very last like the level of the tree. So as you see here, in the here we have only 2 like the nodes, and here is double, so it becomes 4. So it is twice the number of nodes that we have in the previous level. So same for the T4. As you see here, we have 8, here we have 4, here we have 2, and here we have 1. That exactly each level is twice its previous one. So that means the number of nodes in a complete binary tree with a height of k plus 1 is exactly the number of nodes that we have in a complete binary tree of size k, which is to the power k and minus 1, plus twice the number of nodes that we have at the very end. And as you look at here, it was exactly the number of nodes at the very last level was equal to the power h minus 1. So here is going to be 2 to the power k plus 1 and minus 1. K plus 1 minus 1. So we're gonna like to just simplify this one. It's gonna be to the power k plus to the power k minus 1. We can use the to the power k as a common factor, so it's gonna be twice to the power k minus 1, which is equal to the power k plus 1 minus 1. Now that we are done with the right side, we're gonna write show the left side. So I'm gonna just write the left side for h equal to k plus 1. It is sigma of I equal to 0 up to k plus 1 minus 1. And again, I just replace h with k plus 1 of to the power I. So I'm going to write it or simplify it. It's going to be equal to I equal to 0, sigma of I equal to 0 up to k to the power I. And is k because k plus 1 minus 1, we can just see that 1 plus 1 minus 1 is going to be 0. So here this is equal to, I'm going to just extract some sentences or some expressions from this like the sigma that I have here. So it is equal to sigma equal to 0 up to k minus 1 of to the power I. So I'm just taking the expression when I is equal to k. When I is equal to k, I can write to the power k for this case. So let's look at this one that I have here. Based on the induction hypothesis, this is equal to the power k minus 1. So I'm going to write to the power k minus 1 plus to the power k. And again, it is equal to 2i's to the power k minus 1, which is equal to the power k plus 1 minus 1. As you see here, the both left side and right side end up with the same like the expression, which is to the power k plus 1 minus 1, which proves our theorem. So that's about the like the number of nodes in a complete binary tree, and which is equal to if the height of tree is h, then the number of nodes is equal to the power h minus 1. So we can see that if again h is if n is equal to the power h minus 1, then we can see that h then it is equal to the logarithm of n plus 1 in the base 2. So which again will be used later when we're also going to talk about the binary search trees.